All right, this is Riley Wall. She's here to pretend like she's one of my students, being how the pandemic has destroyed my ideas for doing this. So she's going to do the lab for me. She's a former student and got an A this last semester in her chemistry class. So she's a good one to step in to do this. First thing she's going to do, we're going to do a lab on determining freezing points, depression constants. For using sodium chloride. So the first thing she's going to do is she's going to take a 600 cc or 1 liter beaker, and she's going to fill it half full of ice. And then she's going to put water in there to the halfway point. And then she's going to take the temperature of that water to see what that is according to the thermometer, not to what it actually should be. Now, while she's doing this, I'm just going to give a little commentary here what's been going on. Since we started the school year, we've not been able to have anybody work together in pairs. This is a lab I had devised for one person to do at a time. When they got done with a particular set of lessons, they were going to come in here and do this. Obviously not happening now. But she's right now measuring the temperature of the water. Riley, why are we doing that? Why don't we know already it's supposed to be 0 degrees?
Yeah.
But why are we doing it?
Exactly 2 0
Okay, so I don't know if you could hear what you said, but what you said was actually correct. The problem with these thermometers is they don't actually say 0 when it's supposed to be 0. They're slightly off, so we have to calibrate accordingly. And after she gets done with that, she's going to get a 150 cc beaker and pour 50 cc's of distilled water into that. And then she has already measured out her sodium chloride. She has 22 grams of sodium chloride. And then she's going to stir until that is completely dissolved. Okay, she's now getting her 50 cc's of distilled water, and she's about to pour that into her sodium chloride, or 22 grams of it. In which case she's going to stir it till it's completely dissolved, which will take a little bit of time, so we're not going to watch her do the whole thing. While Riley's stirring it, trying to get the stuff to dissolve, we'll just describe the next step that you should be seeing. She's going to put the beaker of water into that giant beaker of ice water, and she's going to measure the temperature which it starts to freeze. This will take a while. She'll be recording each minute's temperature until it stops going down, and then we'll go from there. Okay, she's done stirring now. Now she's going to try and get the beaker stable. She may have to put more ice in there just to make sure that, it's floating. That's good. Yeah. So now she's going to let it sit for a while before she starts taking the temperature. And once it starts to get, let's say about 5 minutes, she's going to put the thermometer in there and leave it in there while it's slowly decreasing in temperature. In theory, it should go above or below 0, Riley?
Above. Like below, sorry.
Because?
The crystals.
What about them?
They take longer to freeze. Because it has more.
Right, it's got the solute will get in the way of the formation of crystals, right? All right, good. Okay, so we won't watch this for 5 minutes. We'll come back in just a little bit. Okay, at this point, Riley's been waiting for things to equalize out. Now she's put her thermometer into the small beaker that's inside the large beaker. And what's the temperature at right now?
8.
-8 or +8?
Negative.
-8. So it's doing a good. What was the original temperature you had?
0.2.
0.2. Okay. So it's already dropped well over 8 degrees. And it'll probably take a little while more before it stabilizes out. So I'll pause at this point as well. Okay. So it's been a couple of minutes. What's the temperature at now?
4.
4? So it's gone up?
No, it was at 5 before it's gone down.
You said 8.
Yeah, it was at 8. So then it went down to 4.
But that's going up. 8 below is lower than 4 below.
Yeah, you're right.
I'm gonna have to cut that part out.
Right.
We'll just say 8 below.
Okay, what's that? We'll just say 8.
All right, good Lord. Okay, at this point then,
Because the only thing that changed for me was the .2.
what changed?
My original temp, it was at .5 before, but now it's at .2.
Okay, so original, so now we're gonna figure out the KF for this, which is the freezing point depression constant. And by plugging in for the formula, and I'll put this in on the screen, that the freezing point is equal to the original freezing point minus the molality of the solution, which we'll talk about, times the KF, which is the constant, times I. Now I is the Van't Hoff constant. What's the Van't Hoff constant here?
2, because NaCl breaks off.
Right, NaCl breaks down to 2, so I is 2. The I is the number of particles that goes into solution. And how do you find the M? What do you have to do for that?
Well, you have to take the 20 grams of NaCl, find the moles, and then you take the moles over the water.
How much? What?
It's 0.342 moles, then you divide that by 0.05
Kilograms. Okay, so it's moles of solute over kilograms of solvent, and the solvent here, of course, is water. And then we do that, and then we'll talk about the final aspect of this. So Riley's calculated, according to what she just told me off camera here, that the molality was 6 point what?
6.84.
6.84 moles per kilogram.
Yeah.
And the original freezing point you said was 0.2?
0.2.
And then the freezing point was -8, okay? And so she's going to use her algebra skills, because FP equals the original FP minus M times KF times I. She's going to then divide or subtract the original freezing point and then divide by -M times I to get the KF, which she's doing right now feverishly. And then the KF, also known as the freezing point depression constant, is what you come up with.
KF equals 0.599.
Say it again, I can't hear you.
0.599.
0.599, okay. So what'd you get for a KF value?
0.599.
0.599, what's the label for that?
Degrees Celsius mole per kilogram.
You're right, okay, so, you know, and that's the thing about constants, their labels are meaningless, except they equate two variables together or more. Like if we look at Puvnert's, the R there has 4 variables in it, but
Right.
for this one it's only 2. Now what we need to do is find the error. So take that number and subtract what it should have been, which is 1.86 degrees Celsius per mole per kilogram.
1.26. That's what that answer is after that.
Okay. And
1.2636.
okay, 1.26, 3 significant figures, okay? And then we want the percent error, so take that error and divide by the actual KF value.
Like about what I got?
Yes.
Okay.
Well, take the one you get, no,
By the actual?
by the actual, right. You want to see how
1.2.
far off from what you should have gotten. Then take that times 100.
Okay. 67.7.
Yeah, I thought it's about 2/3 off. Yeah, that's about right. And that's high school chemistry for you, because
Right.
we buy the worst materials possible, the cheapest materials possible, And that's why they so look forward to college, to get actual numbers that work unlike these. So thank you, Riley, for doing this for me. I really appreciate it, and I hope everybody got a taste as what it's like to have a lab here at Riverdale.
Right. Hopefully you want to donate some help.
Okay. Thanks a lot.